Our study of biomechanics takes us to linear kinetics, and the word kinetic should elicit in you an understanding that that's a study of forces, both internal and external forces. To regain our context, you know that the physics of mechanics includes statics. Look to the left here in this portrayal. These are the studies of permanent structures, bridges, buildings, roads. And our keen interest is in dynamics. We've spent some time studying kinematics, which has to do with time, displacement, velocity, and acceleration. There are linear expressions of that and angular expressions of that. We turn our attention now to kinetics, which is the study of forces, and likewise there are linear and angular components to that. So kinetics is the study of forces that produce or change motion, and force is defined as that which pushes or pulls through direct mechanical contact or through the action of gravity to alter the motion of an object. That object could be the body or something that we're manipulating in our world. Internal forces we've studied a great deal. This is really the work of the dynamic tissue of muscle, which through the electrical phenomenon can contract concentrically, eccentrically, isometrically, changes the body and its position for the purposes of maintaining our safety, effectiveness, and efficiency. External forces are multifarious. Here are some examples of that. The kids on this ride are enjoying the positive outcomes of gravity. They've got to have the right thing to sit on, so the coefficient of friction allows for gravity to have its full impact. This competitive kayaker uses the force of the water and his own strength in order to successfully navigate the slalom. And then we're students of friction. There are times when cleated shoes are appropriate and times where there needs to be increased friction. And there are times when we want as little friction as possible, like when we're snow skiing or ice skating. And then certainly these two boxers are expressing force and with certain desired outcomes for one of them. The understanding of force is that it has magnitude, how much force is there, the point of application, and the direction of force. So if you look at these various expressions of the application of force, if force is applied right directly through an axis of rotation, there'll be linear motion. If it's applied eccentrically away from the axis of rotation, it will cause a rotation. And so we'll study more about that as our focus moves into angular motion. Certainly this is an example of children intuitively knowing that to get the merry-go-round to rotate, they don't push through the axis of rotation, but they apply a force in the perimeter. And how fast that goes is directly proportional to the magnitude of the force, the application of the force, and the direction of the force. Again, we'll study that more along the way. Sir Isaac Newton helped us understand about kinetics. In the linear expression, Newton 1 is the law of inertia. Very simply, Newton 1 is inertia. A body at rest tends to remain at rest. A body in motion tends to remain in motion. And the manipulation of mass and acceleration will result in force. So Newton 1 is the law of inertia. There's an application of this coming here and also in your assignment for out of class. The second law of Newton is the law of acceleration, and it's a manipulation of the formula of force equals mass times acceleration. So it goes like this. Acceleration is directly proportionate to the force applied, and indirectly proportional or inversely proportional to the mass. So if you want to accelerate something, have big force, and the mass that needs to be accelerated, if that mass is small, then acceleration will be a greater amount. In the case of these books, if the mass to be accelerated is one book, then it would have a certain acceleration. If it's two books, it would have a smaller acceleration because the denominator would be larger. I'm sure hoping this continues to record. I'm trying to reconnect here. I'm just going to keep going. Reconnect. Come on, baby. We'll just do this. I think we're back connected here, and we'll forge ahead. The units of measure for mass are kilograms. The unit of measure for force is newtons, and that's expressed. A definition of a newton is 1 kilogram of weight times 1 meter per second squared, which is acceleration. And so 1 newton is a combination of mass and force in its expression. And then here we go for an application. What advantage does the big man have? He's able to generate tremendous force because his mass is so big, and he's able to accelerate. We think, oh, the poor little guy is in terrible straits. But if you work for not force, but you work for acceleration, because the little man's mass is so small and he can generate force, it may be that he can stay away from the big man and wear the big man out, get him out of balance, and a very small force can be used to push him over. In creating these slides, I got intrigued by the early days of sumo. I guess these weren't the first days of sumo, but here are sumo wrestlers then, and here are sumo wrestlers now. These men are very, very huge and have tremendous capacity to generate force. They may not be real quick, but the purpose is to push their opponent out of the salt ring, and they can do that through just a bull rush or through getting them rotated. And then Newton 3 is the law of reaction. You can see several examples here. I think the one you identify with most is a balloon that is filled with air and then released, and it goes on a reactive journey through the air. The space shuttle action is the propulsive force of the gases that are escaping, and then the reaction is going heavenward. And then in the rowboat, the action is oar in the water and the sailor pulling back on that, so the reaction is actually the travel of the boat. But how about this on your next date at the lake without an engine? Stack that stern of your boat with old cannonballs and push them out. You get a reaction that would propel you across the lake and probably establish a reputation for you. Here are two more examples of action and reaction. If you look closely, this volleyball player who has tremendous angular force generated to strike the ball, the reaction is that he bends his knees so that he doesn't tumble into a total body rotation into the net. So action above, reaction below. And then this long jumper into the pit, here comes her force under the influence of gravity, and the earth pushes back up against her. This can be an issue of safety, and the person needs to have plenty of stabilizing of force around her joints to stay safe and to have strong enough skeleton to manage it. And then momentum, which we've talked about before, is defined as the quantity of motion. It can be calculated by assessing mass and velocity. And so momentum is how much is the quantity of motion. And you know that if a movement system gets going, it has a tendency to keep going. That's Newton 1, that's inertia. And so once it gets going, it's got to be acted upon by a vector force to dissipate the force. If it's in motion, it has a tendency to stay in motion. So in Pamplona, Spain, these people with the red scarves who are running with the bulls, if you just consider their movement system as their body, they get to a place where they have a quantity of motion based upon their mass and their velocity, and that all stays the same unless they're doing braking action. But right now that man's running for his life, and if two systems collide, then there'll be acceleration or deacceleration, but the vector sum will be as the two systems collide, the vector sums would be equal to the vectors, and a resulting vector is formed. And then impulse is the longer force is applied to a system, the greater impulse it will have. And ask you in your homework to think about when a small impulse would be appropriate. Think about delicate or precision movements that would require that. I suppose if you were having LASIK procedure on your eye, you'd want the doctor to use very small impulse. So it would be a small force. Time would be variable as opposed to if you're trying to throw a medicine ball for distance, you'd want big force and big time in contact with the medicine ball. And so that concludes our linear kinetic presentation.